if you have a gas that, say you have a membrane or whatever you have that this gas is contained in, there's a tiny pinhole in it, and the gas can move out through that pinhole. Well, the word for that process is effusion. So if you see anybody asking you about rates of effusion, it's really asking about either something that has a pinhole like that, or maybe a membrane made out of pressed metal or made out of ceramic. And so when gas encounters that, it can work its way through the pores and come out the other side eventually. That's called effusion. Now, diffusion is a little bit different. Diffusion is just how fast a gas may move from one location to another, assuming there aren't any air currents or anything like that. So if you have a tube like this, and you put a gas in here, maybe with a piece of cotton, so there aren't a bunch of air currents. This end is plugged with a piece of cotton. The gas will begin to move from here, and eventually, just by its motion that it possesses, it will move to the other side. That's called diffusion. And at any rate, we're often interested in how fast these processes occur. Now, I want to take you back to an equation that we don't use real often in chemistry. If you've taken physics, this equation may look more familiar to you because we tend to focus on it more in physics class than in chemistry class. And it is kinetic energy equals 1/2 the mass of an object times its velocity squared. Now remember, when we measure temperature, though, we're measuring average kinetic energy. We're measuring something that has to do with the mass of an object and its velocity. Now, if you have two objects with the same kinetic energy, in chemistry we would say those two objects have the same temperature. If you have two objects with the same kinetic energy, they may not have the same mass. If they don't have the same mass, they're going to have a very different velocity. Think for a moment about a bicycle and a train. If you have a bicycle and a train, these two vehicles, and they're traveling along at the same velocity, do they have the same kinetic energy? So, in order for two objects to have the same kinetic energy, if one has a greater mass, come on, eraser, you can do this morning. Erase. If an object has a greater mass, these two molecules, let's just talk about molecules for a moment. These two molecules have different masses, but the same kinetic energy. So the one with the greater mass is going to have a lower velocity, right? So there's kind of an inverse relationship between mass and velocity. If you have particles of a gas that have the same kinetic energy, the same average kinetic energy, because they have the same temperature, if you have a greater mass, you're going to have a lower velocity. So out of that, and you can look up the derivation of this formula online. We're not going to take time to actually derive the formula, but it comes up to this formula that you're going to use to solve the problems on your worksheet. And that is that if you compare the rate of one gas to another, I'm just calling the two gases gas 1 and gas 2. If you compare those two rates, they're going to be related to the molar mass of the gases. But the molar mass it's going to be an inverse relationship, so we're going to put molar mass of gas 1 on the bottom here, and the molar mass of gas 2 on the top here. Now, if we took the time to derive this relationship from this equation, we would find that because of this factor right here, the velocity squared, and how it relates to the mass of the object and its velocity, that here we would find that we would need to have a square root sign. So the rates of two gases are inversely proportional to the square root of their molar masses. This is a mathematical relationship that's widely known as Grahms, got an H here, Grahms Law. And you use this formula if you want to compare rates of two different gases, or if you have the rates of two different gases but you need to know the molar mass of one of them. That kind of problem. In fact, let's look at the problem right here on your worksheet. A certain gas effuses 4 times as fast as oxygen gas. What is the molar mass of the unknown gas? So if we're going to just substitute the numbers from this problem into this equation, what would be the rate of the oxygen gas? So I heard a couple of you say 1. That's going to, I'm just substituting the rate for oxygen gas. I'm just going to change this to O2 so we know we're talking about oxygen. What's the rate of the unknown gas? 4. So it really doesn't matter whether that's a rate in meters per second or it could be moles per second if it's the amount of gas diffusing through a membrane, because those units you would see would factor out. Whatever the units are on the top are the same as the units on the bottom, and so they would factor out. So we have a ratio here that just describes how fast one gas is compared to another. And we know then that we can substitute in here the molar mass for oxygen. Is the molar mass for oxygen going to go on the bottom or top? The bottom. So I'm going to change this to an O2. And what is the molar mass of oxygen? And we've got to be a little bit careful here because we're not talking about oxygen atoms. We're talking about molecules of oxygen gas. So we want to probably use 32 grams per mole. And up here we have the molar mass of our unknown gas. So this is often how a Grahms Law equation will be set up, how it will look. And we can just go on to solve for the molar mass of that unknown gas. So, of course, you know that we can rewrite this as the square root of the molar mass of the unknown gas over the square root of 32. What is the square root of 32, by the way? So we're hearing 5.65. Is that what you were going to tell me? Or did you have another question? Okay. You want to do it that way? So you want to square both sides so that we end up with 1 over 16 equals the molar mass of the unknown gas over 32. So if I'm going to rearrange that equation, see if I gave myself any more room to write down here. If we're going to rearrange that equation to solve for molar mass, there's several shortcut steps we could take, but basically we would be doing the cross product theorem. Is that the easiest way to do this? In other words, we have 32 grams per mole times 1, so the cross product right here, equals molar mass times 16. And so we're going to divide both sides by 16. So we divide both sides by 16 so that that factors out. And we have the molar mass is 2. And we have the units, grams per mole. What gas is this? There's only one possibility.